we are going to do a tensile test on a piece of reinforcing bar that's set up in the test machine here, and we'll plot the results on the computer as we go. This is how the sample is gripped in the jaws. If I now press the start, the machine will try and grip hold of the bar, and it will start drawing a load against extension graph. So, we've got stress being plotted here, and extension along here. This little blip is because this bit of the test machine, which is fixed, weighs 10 kilonewtons, and it takes up a little bit of slack in the system there. So this should be a nice straight line as our bar is stretched. We've currently got 22 kilonewtons, so 2.2 tons, 2.4 tons, 2.5, 2,500 bags of sugar, and the sample has moved about 6 millimetres. Most of that movement is from the jaws of the test machine, not the sample itself stretching. And this little jaggedness is as the jaws dig in and slip a little piece as the bar is stretched. And now up to 3.7 tons, 38 kilonewtons, 39, 40. This is programmed to increase by 30 kilonewtons per minute. And the machine will move in order to maintain that rate of loading. Stress on our 16mm bar is at the moment 214 newtons per millimetre squared. We would hope that it gets to at least 500, because our steel is nominally a B500C piece of rebar, and the B500 refers to the characteristic strength of the steel. So we would expect to get to at least 500 plus a bit, and we're currently at about 300. If I took the load off, our 6.2 tons, 62 kilonewtons off now, the bar would spring back to its original length. It's behaving elastically at this point, and obeying Hooke's law. Double the load, double the stretch. .2 kilonewtons, 7.2 tons, 7,200 bags of sugar. Stress of 380 newtons per millimetre squared. .400. So that's 40 bags of sugar hanging off every square millimetre of the reinforcing steel. So at the moment, the iron atoms in a crystal form, the structure is just deforming a little bit. Take the load off, it will spring back, and that's why it's behaving elastically. At some point, that crystal structure gets damaged, and the atoms start sliding past each other, and that's post-yield. Nearly up to our 500. So there, our steel has exceeded its characteristic strength as per its specification. Now we'd expect it to get to maybe 560 or 570. In other words, characteristic plus a bit. Still behaving elastically, but not for much longer. And there we are, there's yield. What's now happening is that crystal structure is being damaged, and we're getting permanent deformation. The machine will start to speed up because it's still trying to apply 30 kilonewtons per minute. Our stress is now up to 630. We're having to put more load on it to keep it stretching. At some point we're going to reach an ultimate stress, and at that point the bar is about to break. So when this figure starts dropping, the bar is about to snap. You can now see it stretched nearly 50 millimetres. Still creeping up, and loads up to 13.4 tonnes now. Still creeping up, but that's about the maximum. Now it's dropping off, and then the bar breaks. And there's our test completed. Our bar has stretched significantly. The piece in my hand here is still cold because that hasn't stretched, but all of this length of bar has stretched in that post-yield section of the test. As it's drawn out, it's got longer and longer, and the cross-sectional area has reduced, and this is now quite warm to the touch. And that's the atoms sliding past each other, generating friction and generating heat. And it's failed at this particular location, probably because there's a very small defect, maybe a little speck of impurity or a micro crack that's concentrated the stress at that point rather than anywhere else on the piece of bar that was stretching. Our bar has gained overall maybe 60 or so millimetres in length before it failed. Almost all of that deformation has occurred post-yield. And there's our tensile test of piece of reinforcing bar.